Hello everyone. Today I got this request from Danusha Raghu to post videos on differential equations and its solutions. Well, let's try to explore this differential equation by solving a simple example. Say you have f of n plus 2 equals to f of n plus 1 plus f of n, with f of 0 equals to 0 and f of 1 equals to 1. Now if you plug in 0 here, you get f of 2 equals to f of 1 plus f of 0. That's when n is 0, right? And because this is 0 and this is 1, you add them up, you get 1 as f of 2. And here's how it goes. You have 0 and 1, and then 0 plus 1 gives you 1. And f of 3 would be 1 plus 1, which is 2. 1 plus 2 would be f of 4. F of 4 is 3. 2 plus 3 is 5. So that's f of 5. 0, 1, 2, 3, 4, 5. Yeah, that's f of 5. And once you start doing this, you realize that this is something you've seen before, which we call as Fibonacci sequence. And that's exactly what we are aiming today. We want to solve this difference equation, which means we want a formula for the Fibonacci sequence. Now you probably have seen this more in a familiar way as an plus 2 equals to a of n plus 1 plus an. That's recursion. It's equivalent to this one because the function, when we write it like this, we're assuming that the function is only defined for natural numbers or non-negative integers. Okay, so that's what we're trying to do today. Now before I start solving it, let me draw some parallels to differential equations because I assume that most of my subscribers know differential equations. So here's a second order linear homogeneous differential equation. In the most general format, it's ay double prime plus b times y prime plus cy equals to 0. If the right side is a function of x, then it's no longer homogeneous, but if it's 0, it's homogeneous. And we want these a, b, c to be constant coefficient. So let me say actually constant coefficient. That's another requirement. Now if it's constant coefficient and second order and linear, actually it doesn't have to be second order, it could be third order or fourth order or whatever, then the general way to solve this is to say that these type of differential equations have e to the rx as a solution. So you plug that in here, and if you do that, you get an equation for r, which we call that the characteristic equation, right? You set that equal to 0. It has two solutions. When r is a complex number, or if the solutions are equal to each other, then the solutions become more complicated. But at least when if r1 and r2 are different, then the general solution of y would be c1 times e to the r1x, because the solution is e to the rx. So we replace r by r1, which satisfies this equation. And then another one, c2 e to the r2x. So that's the general solution. And if it also has some initial condition as something like y prime of 0 is -2 and y of 0 is 1, then you can use that to figure out what c1 and c2 could be. And that's how you solve it. Now, in our case, when we have constant coefficient, second order, linear, homogeneous difference equation, the treatment is very similar to how we solve second order linear homogeneous differential equation. By the way, don't complain that you have so many descriptions. The more description it has, it defines the equation into a very narrow class, which is easier to handle. Okay. So again, if it's like this, in general, what the format looks like: a times y of n plus 2 plus b times y of n plus 1 plus c times y of n equals to 0. Now, the difference equation that we just wrote down, the Fibonacci one, is a special case of that, because instead of f, if we write down y and then move this to the left side, then it's like a is 1, b is -1, c is -1, with y being replaced by f. Okay, so it's basically the same thing. Okay, all right. So for such a case, what we do is, again, instead of solving the differential equation, or solving the difference equation, we make guesses. Okay, and if the guess turns out to be good, then by the uniqueness and existence of solutions of the difference equations, we have nailed down the exact solution. Okay, so that's the idea. See, that was the philosophy in differential equations, right? We don't solve differential equations, we just make guesses, and if we find the solution, then the mathematical theorems of existence and uniqueness handles all the rigorous details of making it rigorous, right? Okay. All right, so anyways, if you plug this in here, then y of n plus 2 would be replacing n by n plus 2. So you get a of r to the n plus 2. This will be r to the n plus 1. This will be r to the n equals to 0. And then you divide everything by r to the n, and you get a times r squared plus b times r plus c equals to 0. So another characteristic equation just like this one, right? Except that when you solve the solutions, if the two solutions are different, then you have r1 to the nth power and r2 to the nth power, again, c1 plus c2, because the form of the solution was r to the n, not e to the rx, it's r to the n. So you replace r by r1 and r2, and you take the linear combination of the two, and that's the general solution. And then to find out what c1 and c2 are, you use the values of y of 0 and y of 1. In our case it was 0 and 1, but if it's different values, you just have to figure out what those are, and those values will determine what c1 and c2 are. Okay. All right, so let's now use this knowledge to solve the Fibonacci difference equation. So f of n plus 2, actually let's write it as the standard form, at minus f of n plus 1 minus f of n equals to 0, and you set y as r to the n, plug that into the above, and you end up with r to the n plus 2 minus r to the n plus 1 minus r to the n equals to 0. Divide by r to the n, and you get r squared minus r minus 1 equal to 0. Well, we could have went from here to straight to this one. But anyways, if this is your solution, then now what you do is you say r is equal to, this cannot be factored, so you have to use the quadratic formula, which says negative b is -1, so it's +1, plus minus square root. B squared is +1 times 4 times 1 times -1, so it's because you have to subtract the -4, you end up adding 4, so 1 plus 4 is 5, so you have 5 in here, and 2 will be the denominator. So you have the two solutions, and that gives you the general solution, which is f of n must be c1 times 1 plus radical 5 over 2 to the nth power, plus c2 times 1 minus radical 5 over 2 to the nth power. Okay, so that's a major result. We are very close to solving the Fibonacci equation. And let's see, we also had f of 0 equals to 0 and f of 1 equals to 1, right? And our solution is that f of n should be some constant times 1 plus radical 5 over 2 to the nth power, minus plus another constant times 1 minus square root of 5 over 2 to the nth power. Okay, now let's try to plug in 0, n equals to 0. That gives you c1 times anything to 0 is 1. c2 times anything to 0 is 1 again. And because f of 0 is 0, you end up saying 0 is equal to c1 plus c2. Okay. And then the next one, you have f of f of 1 equals to c1 times 1 plus radical 5 over 2 to the first power, so it's just 1, plus c2 times 1 minus radical 5 over 2 to the first power, so again it's just 1. And if we it's common denominator, right? So if we put like this, and then it's c1 times 1 plus c2 times 1, so it's c1 plus c2. And the ones that have square root of 5 is c1 and then negative 1 times square root of 5, so it's c1 minus c2 times square root of 5. And then you immediately notice that c1 plus c2 is 0 in the first condition, right? So that's just 0. And this one, because f of 1 is equal to 1, this has to equal to 1. So here's what we have. We have the equation that 1 has to equal to c1 minus c2 times radical 5 over 2, multiply by 2, and you get, and then divide by square root of 5, you get c1 minus c2 equals to 2 over square root of 5. And we're very close because, see, if I rewrite the c1 plus c2 equals to 0 and add them together, you get c1 plus c1, which is 2c1. Negative c2 plus c2 is, they cancel and it's just gone, right? And 2c1 must be 2 times radical 5, so that says c1 must be 1 over radical 5. That means c2, because this says c2 is negative c1, that's negative 1 over radical 5. And put them back, we have the solution. So solution of our Fibonacci series is that f of n is equal to 1 over square root of 5 times 1 plus radical 5 over 2 to the nth power, and then minus 1 over radical 5, because c2 is negative 1 over radical 5, 1 minus radical 5 over 2 to the nth power. Now what's amazing is that if you actually start plugging in 0, 1, 2, 3, 4, 5, somehow, even if the original formula has radical 5s everywhere, they cancel and you always get an integer. So I find that fascinating that you have such a complex looking formula, but when you start plugging in 0, 1, 2, 3, 4, 5, you always get an integer. So that's somewhat interesting. And I hope that this example gave you an idea to how to tackle all the case of constant coefficient linear difference equation, where the two solutions are real and distinct. I'm not so sure if I want to do the other videos for the case when you have double root or complex. If you really want me to cover those, then please like this video, subscribe, and also put a reply, and I'll think about it if I can give you more lessons on this.